My name is Ryan Garrett. I'm going to talk about standing waves and what standing waves would occur in this room. I mostly chose this room because I'm curious to know if there's a note on the marimba that will cause a standing wave. A standing wave is a wave that will fit perfectly between two walls, and that when it reflects off, it will interact with itself. It causes nodes and antinodes. Nodes are points of no motion, and antinodes are points of extreme motion, the maximum motion that can occur. They're unwanted because then it causes unbalanced amplitudes between points of the room. So you could be standing, let's say this is a mixing console, you'd be standing here and you hear a lot of bass, but then you back up over here and you don't hear that much. You don't want that when you're mixing. You can fix them by putting diffusers around the room or making a room that's not perfectly rectangular. But when you do that, you got to keep in mind about reflections of your monitors. So I'm going to take some measurements to see what waves happen. This is 18 feet 6 inches, which is 18.5 feet. This is, looks like 14 feet 6 inches, which is 14.5 inches. And then the height is 9 feet 6 inches, so 9.5 feet. Alright, so the calculations. The calculation to find wavelength is lambda, which is light wavelength, equals velocity divided by frequency. Now we already know what the wavelength length will be because we took the measurements of the room. So we need to try and find out what frequency that has that particular wavelength. So you need to rearrange the equation. So it's frequency equals velocity over lambda. And we're going to use 1,130 feet per second as the velocity. So let's do some calculations. I got 61.08108108, which is 61.1 hertz. Next one, 130 divided by 14.5 is 77.9310348. So it'll be 77.9 hertz. And the last one, 1130 divided by 9.5. which is 118.947368.4, which would be 119 hertz. Alright, so that wraps it up. I hope you learned a little bit about standing waves.